You should follow along for the logistics function. This is in the packet right before day 3, and we introduce this with an example. So suppose we have a particular lake that can sustain a maximum of 8,000 fish. That's the capacity of the lake. And P is in thousands, and T is in years. dp/dt, the rate at which that population is changing, is directly proportional to the number of fish in the lake, to the population, but it's also directly proportional to the proportion of fish that the lake is still not yet holding. So the unused capacity of the lake. So this is one way to write that. I think it's a little bit easier to see if you look at that same equation like this. So dividing through by 8 here. And so dp/dt is directly proportional to P, but it's also directly proportional to the proportion of unused capacity of the fish in the lake. And so that's what this expression is. So you can see the differential equation either way. Okay, referring to the handout, and the first thing you're asked to do is to sketch the particular solution to the initial condition of P equal to 1,000 fish at T equals 0. So these are in thousands here, and if you sketch that solution, always keeping your pen either tangent or parallel to the slope field, you're going to see a graph that kind of looks like this S-curve. This is called a logistics function, and sometimes you see these functions in chemistry. You can see that the population tops out at 8,000. It never actually gets there, but the limit of the population over time is 8,000. So that's the carrying capacity. Okay, from the differential equation, show that the rate of increase in the fish population is greatest when P equals 4,000, halfway between the two horizontal asymptotes. So one horizontal asymptote being P equals 0, and the other being P equals 8, meaning 8,000, and halfway between at 4,000, you're getting the inflection point, and you need to show that. You need to show that dp/dt is greatest, right? The rate of increase in fish population. So you're trying to maximize dp/dt. Pause the video and think about how you're going to do that. Okay. So you're maximizing dp/dt, which means you're going to take the derivative of dp/dt, set it equal to 0, and show that you've achieved a relative maximum. So when you take the derivative of this, probably easiest when you multiply it out to take the derivative, you have to realize that P is dependent on T, so you have to take the derivative of this implicitly with respect to T. So you're looking at the second derivative. When I take the derivative of that, I get K, but times dp/dt, because P is a function of time, and then minus 2K over 8, or K over 4, P, dp/dt. And so you're going to set this equal to 0 and solve for P. Setting that, so first factor it, set it equal to 0, and find that this is always going to be positive because the rate of change of population is increasing. You're going to set this equal to 0 and find that P equals 4, or 4,000 fish. You have to still show that that's a relative maximum, so you can use a number line to do that. You might test P equals 3 and P equals 5 to show that this is positive and negative when P equals 5 and positive when P equals 3, and you're going to achieve a relative maximum of dp/dt when P is equal to 4. Okay. Next question there says, suppose that at time T equals 4 years, the lake is restocked with fish, bringing the total population up to 11,000. So you know that at T equals 4 years, you're up to 11,000. 4, and they want you to sketch in a particular solution. But the main point is that even if you start with more fish than the capacity of the lake, that eventually it still reaches the stable state of 8,000 fish due to environmental factors that we're not considering. Okay, and then you have to solve the differential equation. So, I guess they're asking you to. So, can you give a real world explanation for why this would happen? Overcrowding means some of the fish die out. You guys can think about what some of the reasons would be for it to eventually reach capacity, either starting off with fewer than capacity or more than capacity. Now you have to solve that differential equation and show that this is the general solution. And doing that requires you to do some partial fraction decomposition. So it's really good practice. Pause the video and try this yourself. You're trying to solve this differential equation and show that the solutions look like this. Pause the video. Okay, so you start like this. You're going to separate the variables. You can keep the constant on this side or not. I'm just rewriting the other side. And then you can see that when you integrate, you're going to have to use a partial fraction decomposition. So I pulled out the 8 and wrote the partial fractions this way. And then you're solving for A and B here. You should have found that both of them are 1/8 to cancel off this 8. So it's actually a really nice integral on the left. So natural log of absolute value of P minus natural log of absolute value of 8 minus P at a constant both sides. And then you're going to use log properties here to write this as a single log expression, and then you're going to turn it into an exponential equation. So here's what the exponential looks like. Get rid of the absolute value. Call this another constant, c sub 5, and then you need to solve for p in terms of t here. So multiply through by the denominator, get p on one side, factor p out, and you get this. Dividing everything by c sub 5 e to the kt would give you this, and then you can rewrite that again. So this is another constant, 1 over c sub 5, and then e to the minus kt. So this is the general solution. You can see that the maximum capacity is showing up in the numerator. This general solution is one that you should just know. You're not going to want to go through this process every time, and the logistics function comes up a lot. So maximum capacity is showing up in the numerator, and notice that this limit as t approaches infinity is equal to 8, and we're always getting two horizontal asymptotes, one at p equals 0, one here at p equals 8,000. And that the rate of change of the population will always be halfway in between the two asymptotes. So very generally speaking, the solution to dp dt equaling kp times 1 minus p over m will look like p equals m all over 1 plus c e to the minus kt. This is something that you should know. You should know that m stands for the maximum capacity, and you should know that the two horizontal asymptotes will be p equals 0 and p equals m. Here's a general solution for the previous situation, given that k, the proportionality constant, is equal to 0.8. And then if you knew a particular moment in time what the population was, you could actually find a particular solution. So this is a general solution, and you can always then find a particular solution from that. Often they give you a value for the constant of proportionality. And that's it. You guys can do the homework, and solutions are where you usually find them.